Hello everyone and welcome to this new XGSLab video. In this video we will see the new module NETS, the circuitry calculator that we recently released. So what we are going to do today is to see this kind of grid in which we have, as you can see, a feeder that simulates a network, two transformers that are equal in characteristics and are in parallel. This impedance that connects, we will see basically the earthing system of these two buses. The simulation of the earthing impedance of the substation where the transformers are, two overhead lines in parallel of equal characteristics, a cable line made up of two three-phase group of cables, and in this case a load with a very high impedance, that is to say a no-load scenario. The following scenario that we will see will be exactly this, where we will set a fault, a single phase to earth fault. With this calculation we will be able to see what is the faulted phase current, the neutral current, and also the current to earth. By making a simple ratio, it is possible, as you can see, to calculate the split factor. Then when we are in this scenario, we can also very quickly move the fault at different buses and see what changes in the fault values. Okay, so let's go on. Let's start with this new project. So as you can see, the software is always the same. You have to click New. The name of the file is the one that you want to set. So I don't know, let's video, for example, in this case. Then we have to choose the NETS module. The frequency is in this case 50 Hz. And now, maybe the most important part, the drawing of the model. So let's start by drawing the cells and the buses. So first of all, the cell that will become a feeder, the bus, then we will have O1, 2, and 3 double-sided cells, another bus. Here we have also a single-sided cell that will be the one that simulates the earthing impedance of the substation. Then we have two double-sided cells that will be the overhead lines. Okay, another bus. Now we have one single overhead, one single double-sided cell that will be the one that will simulate the line, the cable line made up of two different three-phase lines. Again, one bus, and the single-sided cell that will be the one for the no load. So now we have the schema basically. So as you can see, if we compare this to this, it is all the elements are present, they are not specified yet, basically. So let's start with specifying the different elements. Maybe we can fit the schema to the screen size, and also we can close this message window. We can start by setting the feeder, so type feeder, name will be feeder, the ports number in this case will be 3, then we have the common transverse impedance. Consider that here you can see the circuit scheme of the cell that you are analyzing. So the ZE is this one, and we can set it, we have to set it in this way with this value, just 0.1 for the real part. The configuration of the impedances are available in 3 different versions. The Cartesian RLC, so resistance, inductance and capacitance, Cartesian resistance, inductive reactance and capacitive reactance, and polar. So here in this case for the feeder we have also to set the different phases. In this case, we have that the voltage, the phase-to-phase voltage is 220 kV. So this means that for this no-load line to neutral voltage, we have for the phase A, for example, we have 132,800 volts. Moreover, we have for the real part 0.13 and 21. Again, for the inductive reactance, we have, as you can see, 2.642. And we can get back to this configuration. Here, then, in order to set all the other ports in a very quick way, you have this button and you can click it 3 times. If you want to set the phases of the different voltages, you can set polar, and here you can set minus 120, and here 120, and that's all. So the feeder is set. Then we can give a name to, well, we can also set the name in a position that we prefer. As you can see, you just have to select the cell, and you have circled, squared in azure the peak points, and also the name can be dragged wherever you prefer. Also the cell can be dragged, and so you can do whatever you want. Let's go on with the bus. The bus number 1 can be named, in this case, FT, and as you can see, according to what has been already set, there is also a table of connection. So as you can see, this shows this table that at this bus it is connected the feeder with the side in, that is the only available for a single-sided cell, and the port 1 of the feeder is connected to phase A, the port 2 to the phase B, and the port 3 to the phase C. Okay. So let's go on with the transformers. When you deal with transformers, you need to recollect the data from the libraries. The libraries are very important for cable, overhead lines, and transformers. For transformers, in this case, we will use this transformer we have set for this example. So, as you can see, you have all the data of the transformers are here, not in the cell. And you just recall this code. So, let's go on with the diagram. So, type transformer. The name is, in this case, trans1. The ports are limited to 2 choices because the single phase transformer is 2 ports, the 3 phases 4 ports. The code, as I said, is TR, and we just have to set the phase for the inside and for the outside, and then we can replace it. Let's set in a more central part the name. So here we have to set a transformer that is exactly like this one. So to do this very quickly, we can use this properties painter. So click on it, select the first one, the one to be pasted, and the second one, and now click with the right button of the mouse, and the copy is made. If we want to set the name, we just have to open it, transfer to, and apply. Okay. Finally, we have to set this connection between the earthing of the FT busbar and of the busbar that we can name already now as TOHL busbar. Okay. And so this is a longitudinal impedance. The number of the ports is 1. The symbol is the longitudinal impedance. The phase in this case is D, because we are connecting the two different, one neutral that is connected to Earth also, and the impedance in this case is 1 milliohm. So this value. Okay. Let's go on again. We have to set the earthing impedance of the substation. So we can open this cell. The type in this case is transverse impedance. The port number also in this case is 1. The name in this case is substation grounding. The symbol is the one for the transverse impedance. Here we have 0, and the phase is D, and the impedance in this case is 1. You can also, just to make a bit more nice the scheme, you can also keep vertical the cell, and we can also in this case set the name in a more tidy way than the default one. And also this cell can be named, for example, Earth connection. So let's go on with the overhead lines. Let's start with this type overhead lines. Port number in this case is 4. There are some general data like the length, in this case is 20 kilometers, and the number of the spans is 80. This means that we have 250 meters for each span. The data for the resistivity of the soil, the permittivity of the soil, the temperature of the line will be kept as in the default. And now we have to set the lines. Also in this case, it is very important the code we can recollect from the library, where all the properties of the line are set. We will see once we have set this line. So the code in this case is C1 for the phases, and so 1, 2, and 3, and it is OH1 for the phase D, that is the overhead earth wire. For the overhead earth wire, we have also to set, in this case, the impedance to earth, that is basically the impedance to earth of the towers of the line, that is 20. Finally, very important, we have to set the location with respect to a common reference for the X and H for each of these conductors. So we have, for example, starting from the lowest one, minus 3.5 and 10.37. For the second one, 3 and 12.37. 14.37, and finally 0 for the overhead earth wire and 21 on 0.5, and we can apply. So in this case we can also rename it without keeping the default name, overhead line 1, and apply, and we can relocate the name, obviously, and also we can go to libraries in overhead lines to see that for the code C1 that we have used, we have kept this kind of line and of conductor, and for OH1 this other kind of conductor. So let's get back to the diagram. This is a perfectly equal line, so also in this case we can use this tool, the properties painter, and also here we can rename this. Okay, now it's time to set the cable lines. So let's click on this, type cable, name, in this case we will set this name, this cable number. The cable number is the number of the single core cables, let's say, in this case 6. So now this has been closed by default, so 6 cables. We have to set also in this case some general data like the length. The length of the cable line is, for example, in this case 10 kilometers. And the 6 cables we have are this one, where the code is UC1. Also this can be recollected from the library and we can copy on all the cables. Also in this case we have to set the location of the cables, so X and Z. We have for this -2 and Z1 -1.5. Okay, and for the cores we can set the phases. For the screens, the D, that is the neutral, and also the connection to Earth, as said. Screen D, core C, screen D, core A. As I said, they are two to 3 phase lines in parallel, so I am beginning again from the phase A. And apply. So also the cable line is prepared. We can also rename this. Can go on by setting this final cell. This is the no load. So for the no load we are going to use a transverse impedance. Let's name it no load. The ports number in this case will be 3. The symbol will be the transverse impedance. The rotation 0. The impedance, the common impedance will be 186, and also the R and just a moment, sorry, I made a mistake with this. Okay, and now we can set. Now everything is ready for the calculation. We can run a debug, compute. The calculation in this module is very quick. So now the calculation is finished, we have this, that is the complete table of the results. Obviously it is a bit difficult to be read, but you can also filter the different columns by maybe the name of the cell, so you can concentrate. Anyway, it is possible to also to make some interrogation in order to read place by place the solution. So for example, let's suppose we are interested just in the current, so instead of keeping selected all of this, we just select the current. We can view this, so we can select one end of one cell, right button of the mouse once the selection is done, and by selecting the angle of the box we can view this. So this is the result for the no load configuration. If we try to analyze also some other positions, so for example the in side of the cable, we can view also this kind of solution. Consider that basically these currents that you can see are due to the capacitive effects in the cable. Unless this effect you could not explain some currents with a no-load configuration. And also the phase can explain very easily that is a capacitive current, since the current is 90 degrees before the phase of the voltage. So this is the no-load configuration, as I said. So well, we could see all these kind of solution for all these kind of cells. We can also view, anyway, another very interesting scenario, that is to say the one with a fault. So we can add a cell that simulates a fault, for example here. And we can set, for example, here a cell for transverse impedance. The ports number in this case will be 2. The name fault. The symbol that we will use will be fault. The common transverse impedance is mainly, as you can see also from this scheme, it is from this diagram, it is the one of the earthing system. So let's suppose we have an earthing system with the impedance of 1 ohm resistive, and then the ports that are connected to the faulted phase, that is to say A, and to the neutral and the earth. So in these boxes, we just have to input the values of the impedance of the fault. So 1 milliohm can be good both for the phase and for the neutral, and apply. We can also keep it straight. So let's go to this. Okay, debug and compute. Okay, so now again, by concentrating our attention to the current, if we click here and fix the box, we can see that we have a phase fault current that is 1220. The current that goes back through the neutral is the D, the one in the phase D, and that is to say 813, and here the current to Earth. So this is the current that we should use in order to size the earthing system that is present where the fault occurs. Obviously, this kind of considerations can be done also in different places of the network that we are studying, for example here, and so we can see easily that the phase A is the one more loaded, and then go on toward the feeder. What is very interesting also is that we can very easily take the fault, take it and place it somewhere else in order to see what is the effect of moving the fault in some other place of the network. So here, for example, if we have a look at the result, we can easily find that now the current that goes to the Earth is much higher than the previous case. This is due to the fact that we have no effect for the phase for the cable screens now. We have the overhead earth wires of the overhead lines that can drain some return current, but here we have no more the effect of the of the screens of the cable. So this is the reason why here the split factor is worse than in the previous case. So let's say that this is the result for the fault current and the division of the fault current. Consider that what is possible to see in this software are also many other things. Let's make an example. For one side of one cell or more than one side of one cell, we can see the phasor diagram. So let's suppose we are interested in the output side of the overhead line 1. So we can go here. We can uncheck this and check this, and we can view the phasor diagram. Here we can see just the current because here the filter is active. But if we put all active, we can see currents, voltages and complex power. Moreover, another very interesting feature for lines and cable is that we can see along one of the port of these lines or cable that we choose the behavior of, for example, or the potential or the current. So let's suppose we want to line the overhead line 1. We add this to this list, and this list is the one that will be plotted. The port that we choose, let's suppose it is the one of the overhead wire. We want to see the potential, and then we can see this. This is the potential along the overhead wire of the overhead line 1. We can see also real and imaginary power part of this potential, and obviously also the current can be seen in this way. So as you can see, Nets gives you many opportunities. Obviously, this is only a very rough presentation. If you are interested in it, do not hesitate to contact us. I hope this video has been useful. See you next video. Bye bye.